Example 11 asks the question, hey, what are you supposed to do when you can't find an antiderivative to help you solve or evaluate a definite integral? Remember, the fundamental theorem of calculus basically says, hey, to avoid the limits of a Riemann sum, all you got to do is find an antiderivative here, plug in your limits of integration, subtract them, and you're good to go. That's going to give you the same exact thing as the limit of the Riemann sum would have. The problem is that we never talked about the antiderivative of an absolute value function. Well, at least I never taught one, right? And you probably never learned one. So what the heck are we supposed to do? Well, here, let me suggest, let's just start with a graph. I'm going to draw some axes here. And I got to draw the graph of an absolute value function, which we know is supposed to be some sort of V shape here. And this vertex for that V shape, it's the x-intercept, right? This would have been a line, would have been some sort of line here, and wherever it hit the x-axis, anything that was down below would have reflect up above it. So whatever the x-intercept is, that's going to be the vertex here. It's not like it is translated up or down any particular number of units. So all I got to do is take 2x minus 1, set it equal to 0, add the 1 over, divide by 2, x has got to be equal to a half. Let me throw some sort of numbers on here. 1, 2. Now let's space them out a little bit more. 1, 2. Yeah, that's good. Right, and right here at 1/2, that's where the point, the vertex of our absolute value function would be. And as a matter of fact, like if I think of this as a linear equation, its slope is 2, its y-intercept would have been ordinarily -1, so down here at -1. But whenever I reflect it up above, it's going to be now a +1 here. So my V shape is going to look like this. Boom. And then boom, right? And I want the area from 0 to 2. Here, let's color stuff in because this is going to make it look pretty. So I want basically that little piece here. And then I'm coming up here from 2. And I want this piece. So in this particular case, it would be really easy to just do this thing geometrically. But I selected this example so that we can see what we're supposed to do in general whenever we have an absolute value function. The idea is to break it up at its little vertex here, and you turn it into two integrals. So the part that's over here on the right-hand side is the regular equation 2x minus 1, because it hasn't been reflected over across the x-axis. But the piece that's over here on the left-hand side, it's the opposite of that. It is, move my iPad so I can write on it a little bit easier. It's negative of 2x minus 1, because it was reflected up above the x-axis. So I'm going to use that additive interval property of integrals, break this up at specifically 1/2 here, and write it as two separate integrals. It's going to look like this. I'm going to find definite integral from 0 to a half of negative 2x minus 1 with respect to x, and then add in the definite integral from 1/2 to 2, and the 2 right there, of 2x minus 1, also with respect to x. And then evaluate each of these things individually. Now, in order to make this a little bit easier here, if I take out this negative sign, I'll bring it out to the front, you'll see that these two things are going to have the exact same integrand. It'll make it a little bit easier to work this problem. So I'm going to pull out the negative, definite integral from 0 to a half, just copy down the rest. Let me do that real quick. Plus half to 2x minus 1 dx. Okay, very good. So let's find the antiderivative of this guy, and I'll only have to do it once essentially, but I'm going to have different limits of integration to plug into each one of these. So negative of antiderivative of 2x minus 1, increase power by 1, it's going to be 2, and then divide by it, it's just going to be an x squared minus an x. And we're going to evaluate that from 0 to a half. That should be pretty easy. Plus, same exact antiderivative, x squared minus x, this time from a half to 2. Okay, all right then. Now let's plug these things in, and then what order do they go in? Which one do you plug in first? Gotta plug in the top one minus the bottom one. And this is always your best friend if you get to do it with 0, because like if it's a polynomial, at least all of that stuff is going to be a whole bunch of nothing. So negative of, we got a half squared, so it's a fourth minus a half. And then I don't have to worry about the 0 because I plug 0 for each of these things. It's going to be nothing. Plus, now we're not quite as fortunate on the other one. Plug in the 2 there. 2 squared is 4 minus our 2 minus, and then I have to do the same thing with the 1/2. 1/4 minus a half. Right, and you notice I put some little parentheses there so I can remember to distribute. All right, and let's simplify. Inside the parentheses here, 1/4 minus a half gives me a negative 1/4. But then multiply it times the negative sign gives me a positive 1/4. Plus, that's just a 2. I'm going to get rid of my brackets and stuff as I go. That's just a 2. Minus, and then we've already done this problem. We already know that that is equal to a negative 1/4, but distribute the negative sign to it makes it a positive 1/4. Add the 2/4 together plus the 2, I get 2.5. Convert that really ridiculous, dumb grade school mixed number into an improper fraction. 2 times 2 is 4 plus 1 more is 5/2. I prefer it that way. And of course, you could verify this. This just happened to be one that you could easily just find the area of each one of these triangles and add it up. As a matter of fact, I would prefer to do it that way because that would be much, much easier than having to do all of these antiderivatives and plug in the things in. But what if it was instead like some sort of quadratic absolute value function or something even worse than that? Whatever it is, you still tackle it with the same exact technique. You just find where those x-intercepts are. Oops. And that's where you're going to break up your function. And anything that got reflected up above the x-axis, you just take the opposite of that and then integrate each of those individual parts.